Hello, this is Joe Neville and welcome to VXLAN Explainer 2. In this video, we're going to be looking at multiple VNIs, the theory, how to configure them, and of course, we're going to go deep and look at the packets in Wireshark. That's the intro, let's get into it. Here's the network I configured in the first video. Link on screen now. If you haven't watched that, please do, because this video will make a lot more sense afterwards. A quick recap, it's a couple of Ubuntu servers that are sat in the same subnet, so this 172.18.1 subnet, and they are separated by two Aruba 6300s here that have a layer 3 link between them, and I configured VXLAN between the Aruba devices so that Ubuntu 1 could ping Ubuntu 2 and vice versa across the layer 3, and I did all of that in a single VXLAN network, so using a single VXLAN network identifier, VNI1. And in this video, I'm going to kick on the design and configure multi-VNI. So this already exists, this is already configured. And what I've done is I've added a new layer 3 interface to my Ubuntu nodes. And I've taken some artistic license here to present this in a clear and uncluttered way. So it looks like there's two servers, but actually this is a single server. These are two different ports on the server. So one sits in the 172.18.1 subnet and sends traffic without a VLAN tag. And the new interface on Ubuntu node 1 sends traffic that is tagged with VLAN 51 and sits in the 172.18.51, and it's a /29. Then over here, same thing again. Ubuntu node 2's got a new VLAN 51 interface, and that is configured in the same /29 with .2. And I'm going to configure the 6300s for the new VNI, so we'll end up with traffic that comes in without a tag will be sent with the VNI set to 1 in the VXLAN header, and traffic that comes in with a .1q tag of 51 will be encapsulated with the VXLAN header VNI marked to 51. And I should point out that while I've gone for a one-to-one relationship between the VLAN and the VNI, so VLAN 1 and VNI 1 and VLAN 51 and VNI 51, you do not have to do that. There's many more VNIs available, so over 16 million are available versus the just over 4,000 VLANs that are available. So it doesn't have to be this one-to-one relationship. I just wanted to emphasize that. Check out video 1 for more details. And to be really explicit about what's going on here, there's only one physical server, one physical link, and one physical port on this side of the 6300. And the traffic as it's sent out across the link is separated by 802.1q. Well, in the case of the first interface from the first video, it's actually the lack of an 802.1q tag, and that is deemed to be VLAN 1 because this port here is a trunk and it's using the default on the Aruba 6300, which has a native VLAN on that trunk of 1, which means traffic that comes in with no tag, that goes into VLAN 1, and then on the new interface, traffic is being sent with an 802.1q tag of 51. That VLAN's allowed on the trunk port, which means that the switch knows that these two packets are from separate networks. So across this link is the 802.1q tag that's creating the traffic separation. Now that's different when we send across the VXLAN configured interface. So if we send across here, it is the VXLAN network identifier that keeps the traffic separate. So VNI 1 and VNI 51. So how do we create this binding between the VLAN and the VNI? How do we create this situation where traffic that's coming in on VLAN 1, so the blue packet here on this interface, will be marked with VNI 1 as it goes across the VXLAN link here? Or traffic that comes in with VLAN 51 here will be marked with VNI 51 as it goes across this link. And as I've said, it doesn't have to be 51 to 51. It could be 51 to 52, 51 to 1051, or whatever of the over 16 million VNIs that you've got. And also, this goes in reverse. You know, this isn't unidirectional that we're talking about. So there's also a binding from VNI to VLAN. The traffic that's coming in, the red packet here, marked with VNI 51, will exit this switch, all things being good, marked as VLAN 51 as it returns. How do we create that binding? Well, no surprises, it's on the switch. I'll be doing this live in a moment. Here's a config snippet to just really emphasize this point. It's under the interface VXLAN 1, we have a VNI that we mark in the configuration, and under that you have a subcommand to link in to create the binding for the VLAN. So we've got VLAN 1 sat under VNI 1. That will create this binding. And also we've got VNI 51, and under that I've got VLAN 51. Okay, that's the design then. I think that's enough about the detail. Let's dive right in and start configuring these devices. Here's my configuration setup, very similar to the first video. Top left, I've got my Aruba 6300-1, top right is -2, bottom left is the Ubuntu Node 1, so this one here, which I've just called UB1. Then we have a diagram of the network that I am going to configure. In the interest of time, I've already done this side, so -2 is fully configured and ready to go, and I'm going to focus on just adding the necessary configuration changes to the 6300-1. So I'll show you the Ubuntu node first. Here's the VLAN.51 interface that I've added in. As you can see, it's 172.18.51.1/29. So that's going to be sending traffic that's tagged with VLAN 51. And let's set off that ping. We'll be pinging 172.18.51.2. So that's going to fail at the moment. I'll show you the config on -2. I've had to add in this new VLAN, so VLAN 51, pointing to the Ubuntu server. I've had to add that to the trunk, as you can see there. So this is the physical port that faces the Ubuntu Node 2. I'm now allowing VLAN 51, of course. And then I have added in a new VNI. So under interface VXLAN 1, we've got VNI 51, the binding with VLAN 51, and then it's the same destination for the vtemp peer.1. Okay, let's jump over to -1 and add in the new configuration then. So I'll go into conf and we do a VLAN 51 to add that in. Now we need to update the physical port that connects to the Ubuntu server. I'll show you that at the moment. That's 1/1/20. As you can see, it's a trunk and we're allowing 1. So we'll go into the command for that port and we do a VLAN trunk allowed and the new VLAN, and I'll show you that. So if we show the config that's on there now, as you can see, this command has just added in the VLAN. It hasn't wiped the existing VLANs that were on there. Now we'll go into interface VXLAN 1. Let's go up to the top then, and we need to go for the new VNI. So VNI 51, create the binding with the VLAN 51 and add in the new vtemp peer. So it's 10.150.99.2. And there we go, straight away we can see we have the successful pings. So the traffic that's coming from Ubuntu 1 that is tagged with VLAN 51 is hitting our physical port 1/1/20, and it's being tagged with VNI 51. That's going across to -2. The VXLAN header is being stripped off and the VLAN 51 tag is being added and forwarded on to Ubuntu node -2, and then the reverse is happening with the echo reply. If I come out of there, let's quickly show you some show interface VXLAN. There you can see we've got the two VNIs, same peer of course, and the binding with the VLAN. If we look in the MAC table, I'll stop this so that we can go into that actually. So which one was it? Here we are. So we're looking for 2FC9A1. 2FC9A1, that's the correct one, isn't it? Yes. So there you can see VLAN 51 locally known via the physical port, and remotely we'll split this and jump over to the other side, to the Ubuntu node 2, and then we can see the MAC address there ends with 24D658. So there you can see that being learnt. So it's VLAN 51, but it's being learnt via the VXLAN 1 port, and we've got the vtemp peer address there, so .2. Close that off. All is looking good, and as we know, the ping is successful. That's the configuration part then working. Let's go deeper and have a look at some packet captures that I've taken from this network. And to sniff the traffic, I'm going to use the same format that I used in the first video, which is where I focused on the non-VXLAN traffic first. So I'm mirroring this port where the traffic is coming in and leaving with the 802.1q tag of VLAN 51, and I've increased the size of the ping again to 100 bytes. As you can see, I'm pinging 172.18.51.2, which is the other Ubuntu server, so Ubuntu 2, which is also in VLAN 51 on the other side of the network. Here's the sample frame then, and as you can see, it's 146 bytes on the wire, and you can see the various headers there. So let's break that down. First of all, we've got the Ethernet header there of 14 bytes. Now this is new because in the first video it was traffic in VLAN 1 without a tag, so now the traffic coming in also has a tag. We're in VLAN 51, so we've got 4 bytes there. Then we've got the IPv4 header of 20 bytes, and as you can see, it's the source and destination of the Linux servers. And then we've got the 8 bytes for the ICMP v4 header for an echo request. I've added those up, 14, 4, 20 and 8, that comes to 46 bytes. Add that to the 100 bytes of the ping, and you get our 146 bytes. Okay, so let's move over then and mirror the port which is on the VXLAN side so that we can see the VXLAN encapsulated traffic. And here is a sample frame. As you can see, it is 196 bytes on the wire. And to drive home what's going on here, this is the outer header. So from the Ethernet header down to the VXLAN header. And then this is the encapsulated inner header here. And something that I think is worth going into some more detail here is the fact that the inner headers do not have a VLAN tag. So we've got the Ethernet being encapsulated, we've got IPv4, and we've got ICMP v4. Now let's compare that to the traffic that's coming in on the non-VXLAN side. Here's a capture from the previous slides. So we've got Ethernet, we've got the .1q tag in there, as you can see, with the ID of 51, of course, the IPv4 and the ICMP v4. So we've got 4 headers coming in, but only 3 being encapsulated. This one, the VLAN tag, has been removed. And I think that's quite interesting because the VXLAN switch here, the VTemp, isn't just doing a simple encapsulation of the traffic that comes in on the non-VXLAN side. So we don't just take this frame and then put the necessary headers like the UDP and the VXLAN headers to send it across the VXLAN network. The VTemp actually removes the tag, and this is in accordance with the RFC. So let's have a look at that. Here's the RFC then, so 7348, and this is the snippet that's relevant to us, 6.1 inner VLAN tag handling. Okay, that's exactly what we're looking for. So the rules are inner VLAN tag handling in the VTemp and VXLAN gateway. In this case, it's the Aruba 6300, should conform to the following. Here we go with the rules then. Decapsulated VXLAN frames with the inner VLAN tag should be discarded unless configured otherwise. Thus, it's dealing with the receiving side first, and it's saying the receiving VTemp, if you get a VXLAN frame that arrives with an inner VLAN tag, unless you're configured otherwise, discard it. And then we move on to the encapsulation side, so the sender side. A VTemp should not include the inner VLAN tag on tunnel packets unless configured otherwise. That's what we're seeing. When a VLAN tag packet is a candidate for VXLAN tunneling, the encapsulating VTemp should strip the VLAN tag unless configured otherwise. So sending VTemp, do not include the inner VLAN tag unless you're configured otherwise. Thus, we're seeing this default behavior of stripping the VLAN tag, but the RFC does leave the door open for configuration options for the inner VLAN tag to be included. But then on the receiving side, if you're not configured otherwise, if you don't have special configuration about how to handle that inner VLAN tag and you've just received a VXLAN frame with an inner tag, then just discard that. Now that we know that we conform to the RFC, let's have a closer look at the headers in this frame then. I've broken it down again, and this is very similar to the first video. So we've got the 100 bytes of the ping, but we see 196 bytes on the wire, and I've broken that down. So we have the outer Ethernet header of 14 bytes. We've got the .1Q tag of 4 bytes. Remember, that's just for this link because this is in VLAN 99. Then we have the outer IPv4 header, which is the source and the destination of the vtemp, so that's 20 bytes. Next up is the UDP, that's 8 bytes. The VXLAN header, again 8 bytes. And now these are the inner headers. We've got the inner Ethernet header of 14 bytes, the inner IPv4 header of 20 bytes. And you can see that's a different source and destination there from the first video because we're now pinging those ports that are in VLAN 51. And then finally, we have the inner ICMP v4 echo request header of 8 bytes. If we add all of those up, that comes to 96 bytes. We combine that with the 100 bytes from the ping, and it comes to, of course, 196 bytes. Moving on to the VXLAN header then, so that we can have a closer look at what's going on with those 8 bytes. Now, the flags are all set to 0, except for the 5th bit, which is the I flag, set to true, because we've got a VNI. And there we can see the VXLAN network identifier, the VNI, set to 51 in this case. And I've just added in this snippet here so you can see this is where we configure the VNI. So interface VXLAN 1, we have the VNI configured there. And now for something a little bit different, we're going to send some IPv6 traffic across the VXLAN network. So IPv6 over a v4 network. Now I've configured IPv6 addresses on the Ubuntu nodes. I'm using the 2001 DB8 51:1/64, and I've got ::2 over here. Let's just focus on VNI 51. And the point is that the vtemp, so the Aruba 6300s, are acting at layer 2 for the traffic on this side. And what that means is that the traffic that's coming in, it doesn't have to be IPv4. It can be IPv6 traffic, which is then encapsulated in an outer IPv4 UDP packet to be sent across the v4 network. So let's jump over to the configuration to show you this in action. Same screen setup as before. Here's the v6 address on the Ubuntu Node 1 server there, UB1. So let's have a look at the configuration. What have I done to the configuration to make this work? Well, nothing. I've not had to do anything. That config is the same. In fact, if I do a show IPv6 interface, it's not enabled because the 6300 is acting as a switch rather than a gateway for this type of traffic. We don't need v6 enabled. Of course, you should always have v6 enabled, but for illustrative purposes, we don't have it turned on. And then, of course, if I do a show IPv6 neighbors, if I can spell that, yep, there's nothing there, of course. Same on the other side, show IPv6 interface, not enabled. Right, so the ping command is slightly different because we need to do a ping 6 up the size to 100, and I'm pinging the other Ubuntu node across the v4 VXLAN network. So will this work? Of course it does, or I wouldn't be showing you this. There we go, so successful IPv6 being sent, hitting the 6300, being encapsulated within v4 VXLAN and sent over, decapsulated and sent on its way, hitting its v6 target. Well, that's the configuration, or lack of, should I say, to enable IPv6 to be transported over an IPv4 VXLAN network. Let's have a closer look at a v6 packet, and it should come as no surprise that this is a little different from a v4 packet being transported. And as a reminder, I've included a v4 packet from earlier. So it's a ping 6 with the size of 100 bytes to a v6 destination address. And I've broken that down. So it's 166 bytes on the wire. Remember, the v4 was 146. Going through those, we've got the 14 bytes of the Ethernet header. We've got .1Q, 4 bytes. We've got the IPv6 header of 40 bytes. So that's the extra 20 right there. As you can see, source and destination being the Ubuntu servers. And then we've got the IPv6 echo request header, which is 8 bytes. Add all of those up, it comes to 66 bytes. Combine that with the 100 bytes from the ping, and it comes to, of course, 166 bytes. Moving on to the VXLAN side then, so it's 216 bytes on the wire versus 196 bytes for a v4 only VXLAN packet. And the outer headers here, well, these are just IPv4. So the source and the destination address, as you can see, are v4. That's being the vtemps, of course. It's the inner headers that are different. So with the IPv6 source and destination here being the Ubuntu servers, and then we've got an ICMP v6. This is an echo request header as well. Breaking that down then, so 216 bytes, or the outer headers of what we've seen a number of times before. So outer Ethernet header, .1q, outer v4 header being 20 bytes, UDP, VXLAN, and then it's the inner headers that are different. So the inner Ethernet header, okay, so that's the same, 14 bytes, but the inner v6 header, that's 40 bytes, and then we've got the ICMP v6 echo request header being 8 bytes. Add all of those up, that comes to 116 bytes. Combine that with the 100 bytes from the ping, 216 bytes. So the extra 20 bytes are coming from the encapsulated inner IPv6 header. To finish up, let's do some live packet capture. And to start with, I'm going to circle back to IPv4. I've logged into the Ubuntu server 1 twice, and I'm going to set off 2 pings, one to 172.18.1.2, so going across VLAN 1, and the other one will go to 172.18.51.2, utilizing the different VNIs. But first of all, we'll sniff the incoming traffic here. So let's set that off. Off it goes. Okay. Bring up wireshark. Okay, so we've got plenty of packets there already. If we look across those, so I've got some with no VLAN ID. For us, that will be VLAN 1. And then I've got echo request and replies in VLAN 51. You can see the difference. Of course, it's the 4 bytes for the tag in the length, destination and source address being the Ubuntu servers, and 51 there is different, so we can see the tag, and we've got the third octet being different. And now swap over the mirror session. Pings are still running. Start this up again. Maximize that. Okay. And as you can see, right, that's enough, I think. We'll stop that. Everything's in VLAN 99, of course, because that's the one between the two vtemps. And I've added an extra column here, which shows us the VXLAN VNI. So you can see that we've got VNIs of 1 and 51 here. There, if we look at this first one, a request, VNI 1, of course, if we open that up, we see 1. And then look at a request which is in 51. It's marked there with the VNI 51 in the VXLAN header. Other than that, the outer headers are largely unchanged between the different VNIs. It is the inner header, the inner IPv4, which is different. So 172.18.1, and if I look at 51 there, you see 172.18.51. Let's have a look at some IPv6 packets next. I'll do a ping 6. Up the size, 51::2, send that. Back on Wireshark then, so we need to change the filter to IPv6, done. Okay, so we've got lots of packets there. Let's stop that and have a look at a sample. There's a request, and as you can see, we've got the IPv4 outer header for the vtemps. We've got the UDP, VXLAN. There's our VNI of 51. And then the inner headers with our IPv6 source and destination for the servers. There we are, source and destination. So all looking good for v6 over v4. If we check a reply, of course, the outer source and destination will be in the reverse direction. So .2 first. And again, with the inner IPv6 headers. So : : 2 is the source, and destination is : : 1. Excellent stuff. So that was VXLAN Explainer 2, looking at multi-VNIs. Admittedly quite similar to the first video, but I really wanted to look at that traffic separation and the role that the VLAN tag is playing on one side of the network and the VXLAN VNI is playing when it goes across the VXLAN network. Now in video 3, this is where I think things start getting interesting, because I'm going to be looking at multiple destinations for the traffic, so multi-VTemp. So look out for that. I'm going to start making that soon. But in the meantime, please do like, comment and subscribe, all of those good things. It really means a lot. And it just leaves me to say, my name is Joe Neville. Thank you very much for watching, and goodbye.